A ball is projected vertically into the air from point R, which we can see here on the diagram, so that it will eventually hit the ground at point P. So it's going to go up and come back down again. And that is 3 meters from the base of a 10-meter high light at L. We can see that on the left-hand side of the diagram there. At any time t seconds, when the ball is h meters above the ground, it casts a shadow on the ground at point S, which is over here on the right, at a distance of s meters from the base of the light, as we can see just here on the diagram. At any time t, it can be shown that s times 10 minus h is equal to 30. Using implicit differentiation, show the following. Okay, so we just need to do that process. So we have a product here. So if I say that u is equal to s and v is equal to 10 minus h, then u dashed will be equal to ds dt, and v dashed will be equal to negative dh dt. So ds dt, 10 minus h, that's the v du v du dt, take away s dh dt is equal to 0. So ds dt, 10 minus h, will be equal to s dh dt. So keeping the left-hand side the same, ds dt 10 minus h would be equal to, so if we rearrange this, s can be written as 30 over 10 minus h, and we're multiplying that by dh dt. And so if we take this over to the other side, we get ds dt is 30 over 10 minus h squared dh dt as required. Okay, let's see what comes next here. At t equals 0.5 seconds, it's found the ball is 6.275 meters above the ground and moving upwards at 6.1 meters per second. Part B says, by assuming h double dash t is negative 9.8, show that h of t is 2 plus 11t minus 4.9t squared. So, if we integrate one step, we get negative 9.8t plus some constant. We're told that this is 6.1, moving upwards at 6.1 meters per second. When t is 0.5, so this will be negative 4.9, and that's plus c1, and that gives us c1 is 6.1, add 4.9, which is 11, and therefore h dash t is negative 9.8t plus 11. Integrating again, we get negative 4.9t squared plus 11t plus c2. And we know that when t is 0.5, that h is 6.275. Substitute in, and we get 6.275 is negative 4.9 times 0.5 squared is negative 1.225. 11 times 0.5 is 5.5, add c2, and so all of that gives me that c2 is equal to 2, and therefore h of t is going to be 2 plus 11t, take away 4.9t squared, as required. Part C says, determine the initial speed of the ball's shadow correct to the nearest 0.01 meters per second. So, h dashed of 0 is equal to 11, h of 0 is equal to 2, and that's just coming from the formulas that we have here and here. And then we can substitute into the expression that we had before this one just here, because we now have dh dt and we have the value of h. So that's going to give us that s dash naught is 30 over 10 minus 2 all squared times 11, which if we calculate is 5.15625 meters per second, or to the nearest 0.01 as required, 5.16 meters per second. So moving on, because there's more of this question. The graph of the function ds dt against time is shown below. Point R of this graph corresponds to the ball being thrown into the air, while point P corresponds to the ball hitting the ground. The definite integral from a to b of ds dt dt was evaluated so the area for the shaded region could be determined. The area given here is 13.4258 square units. Determine the values of A and B and describe what this definite integral represents in terms of the motion of the shadow. So, well, we know that h of t is 2 plus 11t take away 4.9t squared. We'll see if that helps at all in a moment. So, it does, because this is ds dt. So when we're here, ds dt is 0. That's going to be at the max height. And then this point here we know is when it hits the ground. So that's when h is equal to 0. So we can get these values from our calculator. What we could do is, one thing we could do is we could go to graph and table and do 2 plus 11x take away 4.9x squared. We can graph that. And just need to play with the axes a bit to get it to show. Let's go from maybe -5 up to 10. And with the y's, let's go from, we'll leave that at -21 and we'll go up to say 50 or something. Should be in the window now. There it is. And we want the maximum. So analysis, gsolve, and max. And here we have our A value at 1.22449. So A is 1.22449. And the B is just when the height is equal to 0. So we'll do analysis, gsolve, and root. And clearly it's the second root that we want. And that's 2.413981. And therefore the integral becomes the integral from 1.22. I think it was 1.22. To 2.41 of ds dt dt, and we know that that is -13.4258 because we were told what the area was up here, and the distance moved towards the light as the ball falls from the highest point to the ground. And finally, because there's even more to this question, determine the fastest rate at which the shadow moves correct to the nearest 0.01 meters per second, and the time when this occurs correct to the nearest 0.01 seconds. Well, we have the DSDT and we can fill it in with a few things now. So underneath here we have 10 take away, and we have the H, which is this. And of course that one's squared. And we also have the DHDT, which is that. So, just simplifying that one step gives us 30 over 8 minus 11t plus 4.9t squared, all squared, multiplied by 11 take away 9.8t. And then all we need to do is put that into the calculator and find the maximum. And we know how to do that sort of thing. So the maximum is 17.47 meters per second. And the time that happens at is 0.77 seconds.